Today we're going to talk about briefly what erosion and deposition are, and then we're going to start in on our first agent of erosion, which is water. So, in general, erosion is the transport of sediments from one place to another. Keyword here being transport. So, when you write that down in your notes, make sure you underline or circle transport. Erosion is when particles or sediments are moving from one place to another. Really important also that you want to write in your notes here, the force that drives all natural erosion or all natural transport is gravity. So anytime you see the word force associated with erosion, make sure you know that gravity is that force moving everything through. So there are four agents of erosion, and these agents are what are naturally moving things around on our surface. They are water, ice or glaciers, wind, and gravity. So gravity is the force, but we also have gravity causing landslides and mass movements, which you can see in this picture here. That would be a transport or an agent of erosion. So there are two W's, wind and water, and there are two G's, gravity and glaciers or ice. Now, as those things are moving, they're eventually going to have to settle or stop moving. And that process is called deposition. So, what you want to remember with deposition is there is no movement, happens after erosion, and this is when those particles or sediments begin to settle to the bottom of a stream, for example. Okay, so specifically today, we're going to talk about the first agent of erosion, which is water. This is the most common agent of erosion, so there's a lot to talk about. But the first thing we will discuss is how does running water transport particles or sediments around? And these are the four ways that you see right there. This can happen through suspension, which means that the particles aren't touching the top or the bottom. They're just kind of hanging out in the middle. So mostly, if you look in this diagram, silt and clay-sized sediments are going to be suspended in water. Flotation is right on the surface. Okay, so if you think about when you float around in a pool, same kind of thing. And solution means they're dissolved in the water. So they can't obviously be seen if they're dissolved in the water. So, and then the last one is traction, which is bouncing or rolling of sediments along the bottom. So mostly our bigger size sediments that can't be picked up by the water are going to bounce and roll along the bottom. So if we watch this animation here, you can see that this stuff hanging out in the middle, that would be in suspension, which would be like your silt and clay. Flotation would be at the top. You can see a couple of these larger size sediments, so boulders, cobbles, pebbles, sand. They're rolling or bouncing along the bottom. And then obviously there would be some in solution, which we can't see in the animation because when it's in solution, it's dissolved within it. So right now what we'd like you to do is in the box below, draw yourself a cross section of the stream like you can see in the picture above and what you just saw in the animation. And go ahead and draw in what sediments would be bouncing or rolling on the bottom for traction, right in solution, flotation, and suspension. Okay, now that we know how sediments are going to move within a stream, let's talk about what affects the velocity of a stream. Okay, and remember, velocity is pretty much the speed at which the stream is moving. So what's really important here, and you want to make sure you memorize this, is that the faster the water is moving in the stream, the larger the particle it can carry. And we've seen this in flood situations where when the water is moving really fast, we've seen some pretty large things moving down our streams and rivers. Velocity is also affected by these two things. First one is gradient. Gradient is our slope of the landscape. So if we have a very steep slope, that's going to cause the velocity of the stream to be higher than something that's really flat or a low slope. Discharge means the amount of water within the stream. So think about when the Susquehanna River has had a lot of water in it. It's actually moving a lot more quickly than when it just has a little bit of water in it. So think of any kind of river or creek that you've ever been near, and when there's a lot of water in it, you probably don't want to cross it because it's moving really really quickly, so the velocity is high. So discharge, how much water is in the stream, more water equals a faster stream. And if you look over here, here's a little person who's measuring the velocity of the stream, and this would just be the instrument, that meter that would record the velocity. So if the discharge is too large, meaning if you have too much water in your stream, flooding can obviously occur, and the faster the water is moving, the more likely you are to create levees or even oxbow lakes. And tomorrow we'll talk a lot more about oxbow lakes, but this is an oxbow lake in this picture, and levees are these depositional features on the side of a river. You've probably seen some man-made levees along the Susquehanna River, but there will also be natural levees to protect the areas along this floodplain. When their discharge is high, you don't want flooding in the area. Okay, the last piece here is looking at page 6 of our reference table. So if you would get that out and look at that, we're going to show you how to use this chart. This chart talks about what size sediment can be carried depending upon what the stream velocity is. So if we look at the bottom here, this is stream velocity in centimeters per second. Make sure you recognize the scale at the bottom. Okay, so if we start here with 1, 5's all the way over here, and then 10 is there, and then 2, 3, 4. They're kind of spread out funny, but there is 10 separate lines within there. And then if you go here, here's 10 and here's 100, so these go up by 10s. So within each, you're going up a multiple of 10 instead of, this would be 11, 12. That's not how it is. This is actually 20, 30, 40, 50. So just be aware of that. On this side, you can see this is the names of the size sediments that we talked about when we did sedimentary rock. And these dotted lines show us the size. So for instance, silt here, the particle diameter is between 0.004 centimeters and 0.006. So if we had a sediment within that size, it would be called silt. Same thing for all of these pebbles, 0.2 to 6.4. That is the size. So let me show you how you're going to do this. If we do the first example here, let's say that our stream is going 100 centimeters per second. What you would do is you would go to 100 centimeters per second. You can use a ruler or a side of a piece of paper, and you're just going to line it up. You're going to stop at this black line. Okay, so you never really cross that black line. You always stop as your point. And then you would see that we're within the pebble area. So the biggest sediment we could carry would be pebbles. So if I can carry pebbles, that means I can carry things that are smaller than it. So in a stream going 100 centimeters per second, stop at the black line, read over, I can carry pebbles, sand, silt, and clay. If I want to know exactly what size sediment that would be, I would go this way and I would read off that specific size. So I'm looking at about here, 3 centimeters would be the largest size, so I could carry 3 centimeters or anything smaller than it. Okay, so what I'd like you to do is there are 4 questions there. Go ahead, pause the video, answer those questions, and then I'm going to give you the answers. Okay, so here are the answers to the questions you should have just done. Range of size for a cobble, if we go here are your cobbles, it's 6.4 to 25.6 centimeters. If the velocity of the stream is 10 centimeters, what size would it be able to carry? So we go to 10, we go up to the black line and stop. We're right there, we go over here, we're right on the 0.2, which is a small pebble or a very large piece of sand. And of course, remember I can carry anything smaller than that. This is just the largest size. What's the range? Well, 0.2 to the smallest, okay, which would be 0.001 there. In general, when a stream is moving at a high velocity, what can you say about the size it can carry? It's a larger particle, right? So we can see that right on this graph. The higher the velocity, the larger the particle. It's a direct relationship. So last thing I want you to do is answer these 3 revisions questions, and I'll tell you the answers when you replay the video. Okay, so for this one, largest particle that a stream can have for 8 centimeters in diameter, 8 centimeters is right here. you are in the cobble area, you slide over, you read up to your velocity, or you could read down. The answer should be B, 200 centimeters per second. For the second one, 75 centimeters per second, we go to 75, we read up, we're looking at pebbles and everything below, so it should be C, pebbles, sand, silt, and clay. And the last one, 250 centimeters per second, is transporting sediment ranging from clay to cobbles. Which transport will be dropped if we decrease to 100? So we're looking at 250, it's carrying cobbles to down, but if we go to 100, we can only carry pebbles and down. So what would be dropped off should be A, cobbles only. So that's our notes for today. You're going to do the water velocity and transport sediment activity. If you didn't get any of these questions right, I would raise your hand and ask a teacher before you begin that activity today.